Hey, Science 30s, and welcome to topic 1.3 of Unit D. We're going to be discussing harvesting chemical energy today. Last lesson, I gave you the lowdown on our great insatiable appetite for doing combustion reactions, burning fossil fuels, burning wood. Today, we're going to be discussing the mathematics behind that. Basically, how do you calculate the amount of energy that's released by a combustion reaction? Well, first of all, I did kind of refer to combustion reactions last day, but let me quickly just kind of recap or review what a combustion reaction actually is. You're dealing with a hydrocarbon that's going to be combined with oxygen. You're then going to get, as a result, you're going to get the release of CO2, water, and you're going to get energy release. These are exothermic reactions because you are getting energy as a product rather than energy being a reactant. And the energy, for the most part, in these combustion reactions is going to be two types that you're going to get at the end of the reaction. You're going to get some form of radiant energy, which would be like light energy. And you're also going to get kinetic energy, which is going to basically cause an increase in temperature. Again, in exothermic reaction, we would expect to see a rise in temperature after the reaction has been completed. So that basically wraps up sort of what a combustion reaction is. And this is nothing new. You've been dealing with knowledge of combustion reactions, again, back to grade 9 at least. So when we try to calculate the amount of energy that's being produced by a combustion reaction, we have to deal with something called enthalpy, which is a great word. It's a great party word, enthalpy. I think I spelled it right. Enthalpy. Well, what is enthalpy? Well, enthalpy, first of all, is designated with the letter H. So anytime you see the word H in an equation, and you will see H quite a few times in these equations today, that is referring to enthalpy. Well, what is enthalpy? Let's see if we can classify what enthalpy is. Enthalpy, and this is sort of a textbook definition. I'm going to get to sort of an easier way to think of enthalpy for combustion reactions in a couple seconds. But the textbook definition says it's energy that's gained or lost in a chemical reaction, and you combine that with the product of its pressure and volume. Ugh, horrible definition. So let's see if we can kind of classify this. When it comes to combustion reactions, what is enthalpy? Let's see if we can kind of make it simpler than that. Well, let's do a couple of things here. First of all, anytime you've got delta, if you're familiar with this, delta refers to a change in. So if I'm dealing with the change in enthalpy in a combustion reaction, essentially what I'm referring to with the change of enthalpy in a combustion reaction is I'm referring to the change in temperature. I'm basically looking for a transfer of heat. I'm looking for that heat transfer that is occurring that's causing the temperature to increase in a combustion reaction. So essentially, delta H is equal to a delta or a change in the heat of the molecules in the reaction. So therefore, in a combustion reaction, we can simply refer to enthalpy as equal to heat. That's the easy way to remember it. In these reactions that we're dealing with for this course, enthalpy and heat are basically one and the same. So that's a much easier way to think about enthalpy. It's just a fancy way of saying heat for these combustion reactions. All right. Now, getting back to the rest of the preamble before I get to the main event, which is the big equation today of Hess's Law. So basically, the change in enthalpy, delta H, equals the heat energy, which is referred to as Q. So when we refer to a change in heat energy, or the heat of the reaction is another way to describe this, delta H is going to be equal to Q, and Q, because it's energy, is going to be in the units of either joules or kilojoules. So that's sort of what delta H is going to represent, that delta H is also equal to the value of Q for these reactions as well. And Q simply refers to the heat of the reaction. All right, that's what that is. Okay. Now you can measure the amount of heat that's produced by a chemical combustion reaction using something called a calorimeter. A calorimeter is, and it's right here on your note page right here. There's they're basically devices that allow the reaction to occur inside of them. You trap all the kinetic energy that's being released from the reaction, and then you can measure that chemical, that release of energy in the form of kinetic energy or heat using one of these calorimeters. And you can use these to calculate something called the delta CH prime, otherwise known as the heat of combustion. So this little symbol here, delta CH prime, basically refers to the heat of combustion, the amount of heat that the combustion reaction is producing. So let's do a recap here. Enthalpy is equal to heat. If I have a change in enthalpy, delta H, that's also going to refer to the change in heat energy or the heat of the reaction. The heat of the reaction is referred to as Q. So delta H also equals Q. Q is measured in joules or kilojoules. And I can then determine the heat of combustion or the heat of the reaction using a calorimeter, or to basically figure out what the specific heat of each combustion reaction is. Now, the good news is that information will already be provided for you in your data booklet, and I'll get to that in about 2 seconds. Right now, if you've got your data booklet in front of you, I would say make sure you got your data booklet with you here today if you haven't already got that. Make sure you got a calculator on you if you haven't got a calculator, because we're going to do some calculations here in a couple of seconds. And if you haven't got the notes up yet on your computer or your device or something in front of you, grab the notes, because I'm going to give you some examples of these calculations we're about to do. They're not going to be up on the board, only going to be in the notes. So maybe pause the video right now if you haven't already got all that stuff ready to go, because here we go. Here's the main event. The main event of this section is something called Hess's Law. Hess's Law is basically, this is what it states, and again, it's a textbook answer, but it's going to basically allow us to figure out what the heat of the reaction is. We can figure out the amount of heat, how much heat is being produced by running this equation. And Hess's Law states as follows. It states that the change in enthalpy, delta H, in a chemical reaction, which is the heat of the reaction for a combustion reaction, is independent of the pathway between the initial and final states. So what we're going to do is we're going to essentially figure out what the heat of reaction is before and after the reaction, and we're going to see what the change in that is. And depending on what the change is, the bigger the change, is it a positive or a negative change, that will determine whether the reaction is either an exothermic or an endothermic reaction. We'll get to all of that here in just a couple of seconds. This is the equation that you need to be familiar with, and thank the living stars. It's right here on the bottom of page 5 in your data booklet, right over there. That is in your data booklet on page 5, but you have to kind of be able to read it. The other good news is a lot of the information that's on that is going to be legend over here. So a lot of that information is there. All that good stuff is going to be over there. Okay, so what have we got at this point? Well, what we've got is this horribly complex equation, which I'm not even going to run you through. I mean, I'm not even going to say it because it's a mouthful to say. But you're basically looking at what's called the energy change of the reaction. So delta RH is what we're trying to figure out, which is essentially, because these are combustion reactions, is going to be the same as delta CH prime. So basically, delta RH is in the case of our equations, because we're dealing with combustion reactions only for this course, that delta RH is also going to be equal to the delta CH prime, which is essentially the heat of combustion. So what we're going to use Hess's Law for our purposes for this course, is to calculate the heat of reaction. Now the good news is this: because these are all combustion reactions, what type of reactions are they? They're exothermic, so they are all going to be releasing energy, so we should have at least a rough idea of what our numbers should come out like, and I will get to that here in a couple of seconds once I run our first example. What does all of this mean? Well, you've got a couple of symbols here, and I'll be honest, I'm right now wondering, I think that's epsilon. I'm horribly embarrassed to say that I think that's epsilon. It's the Greek letter epsilon, which represents the sum of. So I've got my delta RH is going to be equal to the sum of the moles of my products times basically their standard molar or enthalpy heat of formation. All right. So this value here. So let me explain something to you. This equation looks horrible, and it is because it's horribly written. However, it's actually quite simple when you look at the whole thing as a whole. This symbol, this epsilon, just basically indicates that if I've got 3 products, I have to account for all 3 products when I do my calculation. If I have, if I'm really in a combustion reaction, the good news is it's always going to be always 2 products. It's always going to be water, and it's always going to be carbon dioxide, right? But I have to factor them both into the calculations when I run this equation. If I've got my reactants, if I've got 17 reactants, I know I don't, but if I had 17 reactants, I would have to calculate all of the moles of each of my reactants plus my standard molar heat of formation, or my enthalpy of each one. Now the good news is this delta FH prime, or that I don't have to worry about, because on page 5, they give you all of those standard heats of formation right there on the top of the page. So every one is listed on there, except for one. This is how dumb this is. They don't give you oxygen. Oxygen is not on there, which makes no sense because oxygen is always going to be one of our reactants. The good news is, you can jot this on your data sheet, although on a diploma exam or a final you're expected to know this, the heat of formation for oxygen is 0. So oxygen essentially just gets eliminated out of the equation because we're dealing with the number of moles of oxygen times, it's always going to be 0. It's always going to be 0 kilojoules per mole is what we're dealing with for oxygen. So oxygen essentially just gets zeroed out of every single equation. But just so if you're wondering where oxygen is, that's the reason why oxygen is not on the list, because oxygen doesn't have a heat of formation. It's at 0. But you're expected to know that. Otherwise, you're in the exam panicking. Where's my heat of formation for oxygen? It's not there because it doesn't exist. Oxygen doesn't have a heat of formation. That's why it's not there. All right. So what I'm going to do is I'm going to use these heats of formation, plus I'm going to calculate the number of my coefficient in the balanced equation. So if I have a balanced equation of, let's say, this isn't going to be, let's say I got methane. I got methane. And let's say I got methane and oxygen. So I'm going to burn some methane with some oxygen, and I'm going to produce CO2 and water. I have to balance out this equation because it's got to be balanced. So there's going to be 2 waters. That gives me 4 oxygens, and that gives me 2 oxygens here. So I'm going to have 1. So I'm going to have 1 methane, 2, that's a bad 2. I'm going to have 2 oxygens, 1 carbon dioxide, and 2 waters. So my coefficients are going to essentially represent my ends in the equation, which I haven't discussed yet. The ends of my equation are going to represent the moles. So basically the equation is stating this. In order to calculate the heat of the reaction, I have to calculate each of my products. I have to times the number of moles of that product. So in the case of carbon dioxide, in this case, it would be 1. Then I would times that by its standard heat of formation, which in this case would be negative 393.5 kilojoules per mole. So I would take that 393.5 times 2. That would give me the total amount of energy that's being either released or consumed by the carbon dioxide. I would do the same for the water, same for the methane, but again, my reactants are going to go on this side of the equation. Sorry, let me do this again. My reactants are going to go on this side of the equation, and my products are going to go there. So I'm going to subtract my products from my reactants, all right? Let me put this into practice because it is kind of a mouthful to discuss unless I give you an actual example. Here's an actual example that's on the actual slide, and you can take a look at it right now. I've given you this one, so if you haven't got the notes, it's very small text, so hopefully you got your notes up right now. I'm saying using the standard heats of formation to calculate, so use standard heats of formation to calculate the enthalpy change for the combustion reaction of methane. Hey, guess what? I just gave you that example up there. It's going to be CH4 plus 2 oxygen is going to give me 1 carbon dioxide and 2 water. So how do I calculate this? I'm not expecting you to do this right now. So step number 1, I'm just going through the page right now, so hopefully you got your page up and you're following along with me. You're going to need to find the standard heats of formation of methane, oxygen, carbon dioxide, and water on the table found on page 5 of the booklet. And you need to find the number of moles, looking at the coefficients in the balanced chemical reaction. So I've got 1 mole of methane, 2 moles of oxygen, 1 mole of CO2, and 2 moles of water. So once I plug all that in, I'm going to get well, and again, all my values are there. My methane is going to have a delta F HN, or a heat of formation, of negative 74.6 kilojoules per mole. There's 1 mole of that. Oxygen, again, has 0 kilojoules per mole. It does not have a heat of formation, and we have 2 moles there. Essentially, that's going to equal out to 0. Carbon dioxide is going to have a heat of formation of negative 393.5 kilojoules per mole. There's 1 mole of that. And then my water is going to have a heat of formation of 241.8 kilojoules per mole, and I'm going to have 2 moles of that. If I run all of that into the Hess's Law equation, into this equation here, it's all there on the page. Take a look at it. It's right below my fingers right there. I'm going to have essentially 1 mole times negative 393.5 kilojoules per mole for the carbon dioxide, because that's one of my products, because I have to do my products before my reactants. I'm going to add that to 2 moles times negative 241.8 kilojoules per mole. That's going to represent my water. I'm then going to subtract all of that value from 1 mole times negative 74.6 kilojoules per mole for the methane, and I've got 2 moles times 0 kilojoules per mole for the oxygen. So when I plug all that into my equation, what I'm going to wind up with is I'm going to have a delta RH, or a delta CH prime, heat of combustion, of negative 877.1 kilojoules minus negative 74.6 kilojoules. That's going to give me a total value for my delta RH of negative 802.5 kilojoules. That's the answer. That would be my heat of combustion. Now, one thing about all these values that you're going to discover, because these are all combustion reactions, I said they're all going to be exothermic. Well, if you get a negative value for delta RH, if you get a negative value, that indicates that you're losing energy, which means that it's exothermic. It's releasing energy. So there's actually energy releasing from the system. That's an exothermic reaction. So all your values, all your answers for these questions, no matter what combustion reaction I throw at you for these equations, it's always going to be a negative number. If you ever get a positive number, you've done something wrong. There should never, ever be a positive value for any combustion reaction that we do in this course. They're all going to be negative values because, again, all combustion reactions are exothermic, so they're all going to be negative values for your delta RH value. I want you to try one on your own right now. Here we go. Calculate the enthalpy change for the combustion reaction of pentane. Pause me right now. You are going to need to balance this equation, by the way. There is going to be some balancing of the equation. You are expected to be able to balance out a combustion reaction equation. So you're going to have to first balance the equation, figure out all your coefficients, and then figure out all of your heats of formation that are on your page 5. See if you can figure this one out. See if you can do it. The answers are on the page, but see if you can plug away. Pause me right now, and I'm going to go through all the information right now. Starting now. Here we go. Step 1, right at the balanced equation. I get a balanced equation of 1C5H12 plus 8 oxygens gives me 5 carbon dioxides and 6 waters. You need to do that first. You have to have your coefficients to know how many moles of each of the reactants and the products you have. Once I've done that, I'm going to plug all the information obtained from the balanced chemical equation, and I also have to find my standard heats of formation off of page 5 in the data booklet into the formula for Hess's Law right up here. You're going to put your products before your reactants. And again, what I'm going to wind up with in my equation, it's going to be my epsilon n delta F H prime is going to be, I'm going to get a value there of negative 3,418 kilojoules, and I'm going to subtract that from negative 173.5 kilojoules, which will be my epsilon n delta F H prime value for my reactants. I should get a value of negative 3,244.8 kilojoules, a very high number, so it's a very exothermic reaction. Again, the bigger the number, the bigger that negative number is, the more exothermic the reaction is. The closer I am to zero, the more I'm getting closer to a minimal exothermic and moving toward an endothermic reaction if the value becomes positive. But again, the value will never be positive for any of these because these are all combustion reactions and they are all exothermic. Let's finish off today with a little bit of thermodynamics to end off the day. Hess's law has also led to the development of the law of thermodynamics, right? There's the 2 laws of thermodynamics that if you've been in my Bio 20 class, you've learned about them. You learned about these in Science 9 even, at least very rudimentarily. So this has been around for a while. First law of thermodynamics, energy cannot be created or destroyed. It can only be transferred or changed, right? We don't lose or gain energy. We just convert it from one form to another. This is how electrical power plants work. Coal power plants do this, like Genesee over by Wabamun Lake. We talked about this in the electrical unit when we talked about generators and turbines and how these alternative forms of energy or how they work. Sorry, not the alternative forms of energy, but how like a power plant works, right? You're going to take chemical potential energy if you're burning coal, right? Because it's a coal power plant. You're then going to burn that. That's going to create kinetic energy by turning turbines, because of the steam and the heat generated by the coal being burned. That turning of the turbines is then going to create magnetic fields around the generators. And when I create these magnetic fields, that is in turn going to create electrical energy. So in this case, I've got 4 transfers of energy between going from chemical potential energy all the way to my electrical energy that then heads to the home. And then when it gets to the home, it gets converted again, right? The loads on our circuits in our homes are going to convert that electrical energy into heat, into light, sound, whatever we're powering with our electrical devices. So this is not a big stretch based on what we've talked about before. But you should be familiar with the energy transfers as they occur, because that applies here for Unit D, and it also applies back to Unit C when we discussed energy transfer from electrical, in electrical systems, right, or electrical circuits. So this is not a huge stretch. Great little diagram here that sort of sums up the 5 parts of a coal power plant there in case you were looking at that. And the last thing, and this is our final thing for today, second law of thermodynamics says that energy transfers are never 100% efficient. We talked about this already in 1.1 for this unit. That's the efficiency equation. Useful output energy divided by total input energy times 100 is going to give you the efficiency of any device that you're using. Whew, a lot of math today, folks. If you want to quickly recap and maybe see a better job than what I did, watch the video here. It's going to talk about enthalpy and how you calculate enthalpy. It's a great watch if you're having some issues with this whole equation. I would certainly endeavor that you actually, or I would encourage you to watch that video about enthalpy and how you calculate enthalpy using Hess's law. Here's your homework, and there is going to be some calculations today, some math coming your way today, so don't think you're going to avoid it today. Here's your questions for today. Complete practice questions 20, 22, and 23 on pages 493 to 498, and I want you to answer questions 1 to 3, 5, 9 to 10 on page 501 of the Science 30 textbook. That's our conversation for today, ladies and gentlemen. Won't you join me next time when I'm going to delve into the fantastic world of nuclear chemistry when I discuss topic 1.4, harvesting nuclear energy. Until then, thanks for tuning in, and we'll see you soon.